Between 1940 and 1945, Britain's Special Operations Executive deployed over 13,000 agents into occupied Europe to conduct sabotage operations against German military infrastructure. These agents relied on time-delay detonators, devices that could trigger explosives minutes, hours, or days after placement, allowing operatives to escape before explosion attracted German security. Over 3,200 sabotage operations used precision timing mechanisms designed by Swiss and French watchmakers recruited by SOE specifically for their clockmaking expertise. These devices destroyed an estimated 1,200 railway junctions, factories, and fuel depots. This is the story of how watchmakers became weapons makers and how seconds of precision timing determined whether agents lived or died. The copper wire was dissolving. Henri Dupont watched through magnifying loupe as copper sulfate acid ate through the restraining wire inside the time pencil detonator. The wire was 0.2 millimeters diameter, thinner than human hair, requiring steady hands and perfect vision to install. When acid completely dissolved wire, spring-loaded striker would release, pierce detonator cap, ignite explosive charge. The acid concentration and wire thickness determined how long dissolution took. Henri had calibrated this particular device for 2-hour delay. If calculation was correct, striker would release 120 minutes after agent crushed glass ampule containing acid. If calculation was wrong by even 10 minutes, agent might still be at target site when explosion occurred. 90 minutes remained until SOE courier collected today's production batch for overnight parachute drop into occupied France. Henri needed to complete final quality check on 24 time pencils, 12 calibrated for 2-hour delays, 12 for 6-hour delays. Each device required individual inspection under magnification, verification of wire diameter, confirmation of acid concentration, testing of striker mechanism. The inspection process took 3 minutes per device, 72 minutes of inspection work, 18 minutes of margin for discovering and correcting defects, no time for manufacturing replacement devices if any failed inspection. The workshop at Station 9 smelled of copper sulfate, machine oil, and brass filings. Station 9, officially designated as The Firs, occupied converted country house in Welwyn, 30 kilometers north of London. SOE had requisitioned the property in 1940, converted it into research and development facility for sabotage equipment. The estate's isolation provided security for classified development work. Surrounding woodlands concealed the facility from casual observation. Checkpoint at estate entrance controlled access. Everyone entering required security clearance and legitimate operational reason for visiting. Henri was 34 years old, a master watchmaker trained in Geneva, where precision timing was family tradition spanning 4 generations. His grandfather had designed chronometer movements for luxury watches. His father had specialized in complications, perpetual calendars, moon phases, minute repeaters, mechanical functions requiring extraordinary precision. Henri had inherited both expertise and workshop discipline that made Swiss watchmaking internationally respected. When SOE recruited him in 1942, they weren't interested in luxury timepieces. They needed someone who could make timing mechanisms precise enough that agents could depend on them with their lives. His brother Marcel worked as SOE agent in Lyon, conducting railway sabotage operations targeting German military transport. Marcel's last letter, received 3 weeks ago through SOE communication channels, mentioned that precision timing was crucial for operations, that agents needed confidence in equipment, that too many operations failed because devices malfunctioned at critical moments. Henri kept Marcel's photograph on his workbench as reminder that abstract engineering specifications translated into concrete life-or-death outcomes. Every time pencil he manufactured would be used by someone like Marcel, someone placing explosives at German facility, someone who needed device to function exactly as specified so they could escape before explosion. The promise Henri had made to himself was straightforward: create timing devices precise enough that agents would have adequate time to reach safety, but not so conservative that operations failed because delays were too long and German security discovered explosives during patrol. The balance was difficult. 2-hour delay provided good escape margin for most operations. But if agent needed to travel through area with heavy German presence, 2 hours might not be enough. 6-hour delay provided safer margin, but increased risk that German patrol would discover device before detonation. 12-hour or 24-hour delays were even safer, but meant agents had to place devices during daytime when detection risk was highest. Henri's fingers were trembling slightly from 4 hours of continuous precision work. Installing copper wire 0.2 millimeters in diameter required absolute steadiness. Any hand tremor could bend wire, creating stress point that might fail prematurely or might resist acid dissolution longer than calculated. The tremor wasn't from nervousness. It was from muscle fatigue caused by maintaining unnatural positions required for micro-scale assembly work. Watchmakers developed characteristic hand positions and finger strengths from years of manipulating tiny components. But even trained hands fatigued after extended sessions. Around him, 6 other technicians worked on different SOE devices. One bench produced silent killing weapons, suppressed pistols, crossbows, specialized knives. Another manufactured radio equipment for clandestine communication. A third created disguised containers, lipstick cases containing maps, fountain pens hiding compasses, buttons concealing compasses. Station 9 was SOE's innovation hub, where technical specialists solved operational problems that field agents encountered. If agents needed device that didn't exist commercially, Station 9 designed and manufactured it. 5 weeks ago, Henri had manufactured batch of time pencils calibrated for 30-minute delays. The short delay was requested for specific operation requiring rapid detonation after placement. Henri had used thinner copper wire, 0.15 millimeters, to achieve faster acid dissolution. Quality testing had shown devices functioned correctly under controlled laboratory conditions at standard temperature of 20 degrees Celsius. The batch was approved for operational deployment. Agent Violette Sabo used one of those devices during sabotage operation targeting German communications facility in northern France. The operation plan called for placing explosive charge on telephone exchange equipment, activating 30-minute timer, departing facility, and moving to extraction point 3 kilometers away. Violette would have adequate time to leave facility, clear immediate area, and reach extraction before explosion attracted German security. But the operation occurred during February cold snap. Ambient temperature was -5 degrees Celsius. At that temperature, acid dissolution rate slowed significantly. The 30-minute timer took 47 minutes to detonate. Violette waited at extraction point for expected explosion. When it didn't occur on schedule, she returned toward facility to determine whether device had malfunctioned. German patrol discovered her approaching facility, arrested her, interrogated her about sabotage operation. She was executed 3 weeks later after refusing to provide information about other resistance networks. Henri had received classified message through SOE channels. Agent Violette captured during operation. Timer malfunction suspected. Revised temperature compensation protocols. The message was bureaucratic, clinical, didn't mention that human being had died because Henri's timing calculation hadn't accounted for temperature effects on acid chemistry. But Henri understood what message meant. His engineering failure had contributed to agent's death. Temperature variable that should have been accounted for in design specifications hadn't been adequately tested. The failure was technical, but consequences were fatal. The incident prompted comprehensive review of time pencil design. Henri tested devices at various temperatures, documented how acid dissolution rates changed with temperature variation. At 20 degrees Celsius, 0.2 millimeter copper wire dissolved in 120 minutes. At 10 degrees Celsius, same wire took 145 minutes. At 0 degrees Celsius, dissolution time extended to 170 minutes. The temperature variation created 50-minute timing uncertainty across normal operational temperature range. That uncertainty was unacceptable for precision timing requirements. Henri had developed two solutions. First solution used different wire material, lead instead of copper. Lead dissolved more consistently across temperature range because its reaction with sulfuric acid was less temperature-dependent than copper's reaction with copper sulfate. Lead wire provided more reliable timing, but was slightly less precise at standard temperature. Second solution used thicker copper wire with adjusted acid concentration. Thicker wire was more resistant to temperature effects, but required longer dissolution time for same delay period. Both solutions involved trade-offs between precision and reliability. The choice facing Henri now was which wire material to use for tonight's production batch. 12 SOE agents were deploying to France for coordinated operations targeting railway infrastructure. Operations were scheduled simultaneously to overwhelm German security response capability. If one operation succeeded and others failed due to timing problems, German security could concentrate on failed sites, potentially identifying patterns that compromised future operations. All 12 operations needed timing devices that would function reliably despite unknown temperature conditions at various target locations. Copper wire provided precise timing at standard temperature. If operations occurred in moderate weather, copper wire devices would detonate within 5-minute window of specified delay time. This precision allowed agents to plan extraction timing carefully, minimizing their exposure to German security. But if weather was cold, copper wire devices might detonate significantly late, keeping agents in danger zone longer than planned. The precision advantage became reliability problem under temperature variation. Lead wire provided consistent timing across temperature range. Devices would detonate within 10-minute window, regardless of whether operation occurred in warm or cold conditions. But 10-minute uncertainty meant agents had to plan more conservative extraction timing, potentially exposing themselves to greater risk by leaving earlier than strictly necessary with copper wire precision. The reliability advantage came at cost of reduced precision. 12 agents were depending on Henri's decision. He didn't know specific operation details. Operational security prevented sharing tactical information with support personnel. He didn't know target locations, weather forecasts, or extraction plans. He only knew that agents were deploying tonight. Operations would occur within next 72 hours, and timing devices needed to function correctly, regardless of conditions. Making decision without complete information was frustrating, but unavoidable. Operational security requirements meant Henri had to choose based on general principles rather than specific circumstances. The workshop clock showed 14:25 hours. Courier would arrive at 1600 hours. Henri needed to complete final decision about wire material, finish quality inspection of current batch, and package devices for transport. Delaying decision wasn't possible. Production schedule didn't allow manufacturing both copper and lead wire versions for field testing. Henri had to choose one approach, commit production capacity to that choice, and accept that choice might be wrong for some operations. Major Emil Kiefer commanded Gestapo bomb disposal and analysis section in occupied France. His unit was responsible for examining captured SOE sabotage equipment, identifying design patterns, developing countermeasures. Kiefer was 42 years old. pre-war engineering professor who had been drafted into military service and assigned to technical intelligence based on his academic background. He approached sabotage device analysis with scholarly thoroughness, treating each captured device as research specimen requiring systematic documentation and testing. Over past 2 years, Kiefer's unit had examined over 50 SOE time delay devices. He had dissected them carefully, documented internal mechanisms, conducted laboratory tests to understand timing principles. He had discovered that SOE devices used acid dissolution of restraining wire to trigger striker mechanisms. He had identified several wire materials: copper, steel, lead, each with different dissolution characteristics. He had measured acid concentrations, calculated dissolution rates, developed formulas predicting device timing based on observable characteristics. This knowledge created operational advantage for German security. When Gestapo discovered SOE explosives before detonation, Kiefer's analysis could determine how long device had been in place based on wire dissolution progress. If wire was 50% dissolved, device was approximately halfway through its timing cycle. This information helped German security estimate when explosive was placed, potentially identifying when and how agent accessed facility. The timing information contributed to broader intelligence picture about SOE operational patterns. Kiefer had also developed countermeasures. He trained bomb disposal technicians to recognize SOE time pencil design, instructed them to carefully extract devices without triggering detonation, established procedures for safe transport to laboratory for analysis. Each captured device provided additional data about SOE manufacturing methods. Kiefer maintained database tracking design variations, trying to identify whether different workshops used different specifications, whether timing precision improved over time, whether SOE adapted designs in response to German countermeasures. Most recently, Kiefer had noticed temperature effects on timing. Devices captured during winter months showed slower wire dissolution than devices captured during summer. Laboratory testing confirmed that acid dissolution rates were temperature-dependent. This discovery created new countermeasure opportunity. If German security could control facility temperature, they could slow device timing, providing more time to discover and neutralize explosives before detonation. Kiefer had recommended that critical facilities install heating systems to maintain warm temperatures that would slow SOE timer functions. The continuous adaptation between SOE design improvements and German countermeasure development characterized technical intelligence competition. Neither side could achieve permanent advantage. SOE developed new timing mechanisms. German analysis identified their characteristics. SOE modified designs to counter German knowledge. German analysis adapted to new designs. The cycle was endless, driving both sides toward increasing sophistication. Henri chose lead wire. The decision was based on reliability priority. Operations in unknown temperature conditions required consistent timing more than they required maximum precision. 10-minute timing uncertainty was acceptable operational parameter. 50-minute uncertainty from temperature-dependent copper wire was unacceptable. Henri would sacrifice some precision to ensure that all 12 operations had reliable device timing, regardless of weather conditions. The decision was pragmatic rather than optimal. Optimal solution would involve manufacturing 2 device types: copper wire for operations in moderate temperatures, lead wire for operations in cold conditions. But operational security meant Henri couldn't know which operations would occur in which conditions. Manufacturing both versions would require choosing which agents received which devices, decision that required tactical information Henri didn't possess. Universal solution using lead wire was less optimal for any individual operation, but more reliable across all operations. Henri completed quality inspection at 15:35 hours. All 24 devices passed inspection criteria: wire diameter within specification, acid concentration verified, striker mechanism functioning correctly, glass ampule intact. He packaged devices in protective containers designed to prevent accidental activation during transport. Each container held 4 devices separated by shock-absorbing material. Containers were marked with calibration information. 2-hour delay devices in containers labeled A, 6-hour delay devices in containers labeled B. Simple marking system prevented confusion during operational deployment. SOE Courier collected packages at 15:58 hours, 2 minutes ahead of schedule. The courier was Royal Air Force officer assigned to Special Operations Logistics. He signed receipt acknowledging collection of 24 time pencil detonators. Confirmed delivery schedule required getting devices to airfield by 1900 hours for overnight parachute drop into France. The courier departed immediately, driving toward airfield, where RAF Halifax bomber was being prepared for clandestine supply mission. Henri returned to workshop to begin next production batch. His work schedule called for manufacturing 48 devices per week, 24 on Monday and Thursday, delivered for operational deployment within hours of completion. The production schedule was relentless but necessary. SOE operations consumed devices rapidly. Each sabotage operation used multiple devices as redundancy against individual failures. Some operations were canceled after devices were deployed, resulting in devices being destroyed unused. Others succeeded, but required more devices than initially planned. Continuous production was essential for maintaining operational capability. The 12 agents using tonight's devices deployed from RAF Tempsford Airfield shortly after midnight. They parachuted into prearranged drop zones across northern France, linked up with local resistance networks, received intelligence about target locations and security patterns. Over next 48 hours, they conducted reconnaissance, finalized operational plans, prepared explosive charges with time pencils Henri had manufactured. Operations commenced on third night after deployment, timed to occur simultaneously at 0200 hours across multiple locations. 8 operations succeeded completely. Time pencils functioned as specified. Detonations occurred within expected timeframes. Agents completed extraction safely. 4 operations encountered problems. 1 time pencil failed to detonate due to defective glass ampule. 1 detonation occurred 15 minutes late, but still succeeded. 2 operations were discovered by German patrols before detonation. The operational success rate was 67% measured by successful detonations, but 83% measured by agent survival. 10 of 12 agents extracted safely despite operational complications. Henri received operational report 3 weeks after deployment. The report was classified summary that didn't identify specific agents or locations, but confirmed that devices functioned within acceptable parameters. 1 device failure was attributed to manufacturing defect, cracked glass ampule that leaked acid before activation. The defect suggested quality inspection procedures needed refinement. Henri reviewed inspection protocols, added additional checks for ampule integrity, implemented use of magnifying equipment for detecting hairline cracks invisible to naked eye inspection. The continuous feedback loop between operational experience and manufacturing improvements was essential for maintaining device reliability. Field failures prompted engineering analysis. Analysis identified root causes. Manufacturing procedures were modified to prevent recurrence. The improvement process was reactive rather than proactive. Problems had to occur operationally before they could be addressed systematically. This reactive approach meant some agents used devices with undetected problems, but resource constraints prevented exhaustive testing that might have identified all problems before operational deployment. Henri continued manufacturing time pencils throughout 1943 and 1944. Production volume increased as SOE operations expanded across occupied Europe. By autumn 1944, Henri was supervising a team of 6 watchmakers producing over 200 time pencils weekly. Quality standards remained high despite increased volume. Inspection procedures became more rigorous as operational experience identified failure modes. Device reliability improved gradually. Failure rate decreased from approximately 15% in early production to less than 5% in late war production. The strategic impact of SOE sabotage operations using time pencils was substantial. Railway sabotage disrupted German logistics, delaying military transport and forcing expensive security measures. Factory sabotage destroyed production capacity for critical war materials. Fuel depot explosions eliminated stockpiles needed for military operations. Telecommunications sabotage disrupted command and control capabilities. These effects accumulated over months and years, creating sustained pressure on German military infrastructure. Post-war analysis estimated that SOE sabotage operations reduced German industrial production by 5 to 10% during critical periods before D-Day and during advance across France. The reduction wasn't decisive by itself. Germany maintained substantial industrial capacity despite sabotage. But reduction occurred when German military needed maximum production to counter Allied advances. Any degradation of German capability during this period contributed to Allied success. Time pencils were essential enabling technology for these operations. Without reliable timing devices, agents couldn't conduct sabotage safely. Immediate detonation after placement was too dangerous. Agents couldn't escape blast radius in time. Long delay without precise timing created unacceptable risk that devices would be discovered before detonation. Precise timing with adequate delay allowed agents to place explosives, depart area, reach safety, and conduct extraction while device was still counting down toward detonation. Henri's contribution was ensuring that timing precision was adequate for operational requirements. 2-hour delays needed to detonate within plus or minus 15 minutes for agents to plan extraction safely. 6-hour delays needed similar precision scaled to longer time frame. 24-hour delays required consistent performance over extended period despite temperature variations and mechanical wear. Each timing requirement demanded different engineering approach and different quality verification procedures. Henri developed expertise in matching device specifications to operational requirements, balancing precision against reliability, and manufacturing devices that met specifications consistently. After German surrender in May 1945, SOE facilities were closed and equipment destroyed or transferred to regular military services. Station 9 operations ceased in June 1945. Technical staff were released from military service and returned to civilian occupations. Henri returned to Switzerland, resumed work as watchmaker in Geneva, eventually opened his own workshop specializing in chronometer repair. He rarely discussed his SOE work publicly, considering it classified information that shouldn't be disclosed even after war ended. When historians researching SOE technical operations contacted Henri in 1960s, he provided brief interview confirming his participation, but declining to discuss specific device designs or operational details. He maintained that technical details should remain confidential because similar devices might still be used by intelligence services. His caution reflected professional discretion and respect for operational security that persisted decades after operations concluded. Henri died in 1982 at age 74. His obituary in Geneva newspaper mentioned he was master watchmaker, had maintained workshop for over 30 years, was respected member of Swiss Watchmakers Guild. It didn't mention his wartime service with British intelligence or his contribution to sabotage operations that helped liberate occupied Europe. The omission was consistent with Henri's preference for privacy about wartime activities. His family donated his personal papers to Swiss Historical Society, which eventually transferred materials related to SOE work to Imperial War Museum in London. Those papers included technical drawings showing time pencil internal mechanisms, calculation tables for determining wire thickness based on desired delay time, quality inspection checklists Henri developed for manufacturing oversight, and operational reports documenting device performance in field operations. The documents provided rare detailed view of how SOE technical development worked, engineers responding to operational requirements, manufacturing under pressure, improving designs based on field experience, balancing precision against reliability in resource-constrained environment. Imperial War Museum displays original SOE time pencil in permanent exhibition about Special Operations Executive. The device is approximately size and shape of thick pencil, hence the name, containing acid ampule, copper wire, spring-loaded striker, and detonator cap. Museum interpretation explains that device was activated by crushing ampule to release acid, which then dissolved restraining wire over predetermined time period. Display includes cross-section diagram showing internal mechanism and explanation of how watchmaker expertise translated into precision timing device that agents could depend on with their lives. Museum visitors often ask why sophisticated organization like SOE used simple acid dissolution timing instead of mechanical clockwork that would have provided more precise timing. Museum interpretation explains that clockwork mechanisms required maintenance, were susceptible to moisture damage, produced audible ticking that could alert German security, and were too complex to manufacture in quantities required for operational deployment. Acid dissolution timing was simpler, more reliable under field conditions, completely silent during countdown period, and could be manufactured by small teams producing hundreds of units weekly. The trade-off between sophistication and practicality characterized much SOE equipment development. Optimal engineering solutions were often unusable operationally because they were too complex, too fragile, too expensive, or required too much maintenance. Practical solutions that met minimum operational requirements were preferred over sophisticated solutions that exceeded requirements but introduced additional failure modes. Henri's time pencils exemplified this principle: simple acid chemistry instead of complex clockwork, but adequate precision for operational purposes and robust performance under field conditions. Major Kiefer's post-war testimony to Allied intelligence confirmed that German bomb disposal analysis had identified SOE time pencil design and characteristics. Kiefer explained that understanding device timing principles had helped German security develop countermeasures, but acknowledged that countermeasures were only partially effective. German security couldn't prevent all sabotage operations despite understanding SOE technology. The combination of simultaneous operations' overwhelming security response capability, local resistance support helping agents avoid patrols, and continuous SOE design improvements staying ahead of German countermeasures meant that sabotage operations maintained effectiveness despite German technical knowledge. Kiefer's testimony also confirmed temperature effects on device timing. He noted that SOE appeared to have adapted device design to compensate for temperature variation, suggesting that intelligence feedback loop was functioning effectively on both sides. German analysis identified device characteristics, SOE modified designs to counter German knowledge, German analysis adapted to new designs. The continuous cycle validated Henri's concern about engineering failures contributing to operational losses and justified continuous design improvement efforts. The database Kiefer maintained tracking SOE device characteristics was captured by Allied forces and eventually transferred to Imperial War Museum archives. The database documented 53 separate SOE devices Kiefer's unit had analyzed, including detailed technical drawings, chemical analysis of materials, timing test results, and operational intelligence about where and how devices were deployed. The database represented German perspective on SOE technical capabilities and provided valuable historical evidence about intelligence competition between SOE development and German analysis. Comparison between Kiefer's database and Henri's technical documentation shows interesting pattern. German analysis accurately identified device mechanisms and timing principles, but underestimated manufacturing quality improvements over time. Kiefer's database shows device failure rates decreasing from German perspective, suggesting that German analysis couldn't fully anticipate how manufacturing refinements would improve reliability. This limitation meant German countermeasures remained partially effective but never achieved complete suppression of SOE sabotage capability. Henri's brother Marcel survived the war, conducted multiple sabotage operations in Lyon area, eventually participated in liberation of Lyon in September 1944. Marcel never knew that Henri had manufactured timing devices Marcel used during operations. Operational security prevented Henri from discussing his work, even with family members who were themselves SOE agents. The separation between support personnel and operational personnel was maintained rigidly to prevent compromise of technical capabilities if agents were captured and interrogated. Marcel learned about Henri's wartime work only after war ended, when Henri mentioned casually during family gathering that he had worked at British research facility developing equipment for clandestine operations. Marcel asked what kind of equipment. Henri replied that he had manufactured timing devices. Marcel realized that some devices he had used might have been manufactured by his own brother. The recognition created emotional reaction. Gratitude that Henri's work had contributed to Marcel's survival, but also sobering awareness that technical failures in Henri's work could have killed Marcel during operations. The conversation was private and brief. Neither brother discussed it extensively. Both understood that operational security extended beyond wartime even when discussing with family members who had security clearances. But private acknowledgement between brothers that one's technical work had protected others' operational activity created personal connection that transcended abstract appreciation for support personnel contributions. Henri's promise to create timing devices precise enough that agents could escape safely had been fulfilled specifically for Marcel, even though Henri hadn't known Marcel was using his devices operationally. The broader community of SOE technical personnel and operational agents never had equivalent recognition moment. Most agents never knew who manufactured equipment they used. Most technical personnel never knew which operations used their equipment. Operational security prevented these connections from being acknowledged even when war ended. Recognition of technical contributions came through collective acknowledgement rather than individual attribution. SOE succeeded because technical development supported operational deployment, but specific connections between individual developers and individual operations remained unknown. Henri's technical papers include one document that suggests personal awareness of this connection. Among his manufacturing logs is handwritten note dated April 1943. Batch 47, lead wire devices, 6-hour delay for Lyon operations, extra inspection for quality. The note isn't signed, but handwriting matches Henri's other documents. Lyon was where Marcel operated. April 1943 was period when Marcel was conducting intensive railway sabotage campaign. The extra inspection notation suggests Henri knew his brother was operating in Lyon and took special care with devices destined for that region. Whether Henri deliberately sought information about which devices would be used in Lyon operations, or whether operational security breach inadvertently revealed this information is unknown. SOE procedures prohibited such information sharing, but practical realities of small organization with overlapping personnel might have created opportunities for informal information flow. Henri's note suggests he found way to connect his technical work with his brother's operational activities, despite formal security restrictions. The ethical question about whether Henri should have maintained strict operational security, even regarding his brother's safety, or whether family loyalty justified seeking information that operational security prohibited, doesn't have clear answer. Both imperatives were legitimate. Operational security protected all agents by preventing intelligence compromise. Family loyalty was natural human impulse that motivated much wartime service. Henri navigated between competing imperatives by maintaining official security procedures, while taking special care with devices that might be used by his brother. The compromise wasn't perfect from either perspective, but represented practical resolution of conflicting obligations. Imperial War Museum archivists discovered Henri's handwritten note when cataloging his donated papers. Museum staff debated whether to include note in exhibition about SOE technical development. Arguments for inclusion emphasized that note documented personal dimension of technical work, showing that engineers weren't detached from operational consequences, but rather deeply connected to outcomes affecting people they cared about. Arguments against inclusion suggested that note documented potential security violation and shouldn't be celebrated even decades after operations concluded. Museum ultimately included note in specialized researcher archive rather than public exhibition. Archive materials are available to qualified researchers but aren't displayed for general museum visitors. This compromise acknowledges historical significance of note, while respecting concern that displaying potential security violation might send inappropriate message about importance of operational security protocols. Researchers studying SOE technical development can access note and form their own judgments about its significance. The time pencil displayed in museum exhibition represents thousands of similar devices Henri manufactured during 3 years of SOE service. Each device was product of precision engineering, careful quality inspection, and awareness that technical specifications translated into life or death outcomes for agents deploying into occupied territory. Henri's watchmaker training provided technical foundation for manufacturing devices that met precision timing requirements. His personal connection to brother operating as SOE agent provided motivation to maintain highest possible quality standards. Whether specific devices Henri manufactured saved specific lives is unknowable. Operational records don't track individual device serial numbers through manufacturing, deployment, and field use. Success or failure of operations depended on multiple factors beyond device timing. Agent training, intelligence quality, security situation, resistance support, and luck all contributed. Time pencil reliability was necessary but not sufficient condition for operational success. Henri's devices enabled operations but didn't guarantee their success. But aggregate impact is clear. Over 3,200 SOE sabotage operations used time pencils to delay detonation, allowing agents to escape before explosions attracted German security. These operations destroyed over 1,200 targets, disrupted German military logistics, forced expensive security measures, and contributed to Allied strategic success. Henri's contribution to manufacturing reliable timing devices for these operations was real, even if individual device impacts are untraceable. The copper wire dissolving in acid, spring-loaded striker waiting to release, detonator ready to ignite explosive charge. These mechanical components represented intersection of watchmaker's craft and war's necessity. Simple chemical reaction timing complex military operation. Precision manufacturing enabling dangerous mission. Technical expertise saving operational lives. The time pencil was both mechanical device and life-saving tool. Product and promise. Engineering and hope. Henri's workbench discipline, measuring wire diameter, verifying acid concentration, testing striker function, translated into agent confidence that device would work as specified. Confidence enabled operational boldness. Boldness enabled strategic success. Chain of causation from workshop precision to battlefield outcome was long and indirect, but real. Henri measured timing in minutes. Operations measured success in destroyed targets. Agents measured value in lives saved through reliable equipment. Different metrics for shared achievement. The photograph of Marcel on Henri's workbench reminded him daily that abstract engineering served concrete human purpose. Every wire installed, every ampule inspected, every timer tested protected someone like Marcel conducting dangerous operation in occupied territory. Technical work was remote from combat, but connected to combat outcomes through equipment agents depended on. Precision mattered. Quality mattered. Reliability mattered. Lives depended on all three. Precision mattered. Quality mattered. Reliability mattered. Lives depended on all three.